Hi, I'm Bob. Welcome back to the solutions to the exercises for the textbook Microeconomics, Theory and Applications with Calculus, the 5th edition by Professor Jeffrey Poloff. We will solve the problems in section 4 in chapter 16 of Uncertainty. It is Investing Under Uncertainty. If it helps, please subscribe to my YouTube channel. Thank you. Here's exercise 4.1. Andy and Kim live together. Andy may invest $10,000 in Kim's education this year. This investment will raise the current value of Kim's earnings by $24,000. If they stay together, they will share the benefit from the additional earnings. However, the probability is 0.5 that they will split up in the future. If they were married and then split, Andy would get half of Kim's additional earnings. If they were living together without any legal ties and they split, then Andy would get nothing. Suppose that Andy is risk neutral. Will Andy invest in Kim's education? Does your answer depend on the couple's legal status? We use the decision tree to answer the question. We first determine whether Andy should marry. The decision tree shows that if he marries, his expected wealth will be $12,000 because he gets $12,000 in the 50% probability of divorce and $12,000 in the 50% probability of not divorce. His expected wealth will be $6,000 if he does not marry because he gets nothing in the 50% probability of splitting up. Andy is better off with legal marital status. We add an arrow to this path. Next, we consider whether he should invest in Kim's education. If he invests, his expected wealth will be $12,000 minus the cost of $10,000, which equals $2,000. It is better than not investing, in which he gets zero additional earnings. We add an arrow on the invest path. Andy is risk neutral, so his expected utility is maximized when his expected wealth is maximized. As a result, Andy is better off investing in Kim's education and getting married so that he has an expected wealth of $2,000. If he is unmarried, his expected wealth of $6,000 is less than the investment cost, so he should not invest. Let's adjust exercise 4.2. Use a decision tree to illustrate how a risk-neutral plaintiff in a lawsuit decides whether to settle a claim or go to trial. The defendants offer $50,000 to settle now. If the plaintiff does not settle, the plaintiff believes that the probability of winning at trial is 60%. If the plaintiff wins, the amount awarded is X. How large can X be before the plaintiff refuses to settle? How does the plaintiff's attitude toward risk affect this decision? Suppose the plaintiff is risk neutral. Her expected utility is maximized when her expected wealth is maximized. The decision tree shows that the expected wealth of not settling is 0.6 times X. The plaintiff refuses to settle if 0.6 times X is greater than the certain wealth of $50,000. That is, X must be greater than $83,333.3 for the risk-neutral plaintiff to refuse to settle. If she is risk-averse, X should be even higher because we must consider a risk premium for the plaintiff. Let's solve exercise 4.3. Use a decision tree to illustrate how a patient with kidney disease would decide whether to have a transplant operation. The patient currently uses a dialysis machine, which lowers her utility. If the operation is successful, her utility will return to its level before the onset of her kidney disease. However, she has a 5% probability of dying if she has the operation. As the decision tree shows, her utility from operation failure is negative y. Her utility from a successful operation is z. We can calculate her expected utility, EU, and then compare it with her certain utility of negative x from using a dialysis machine. She will choose to have the transplant operation if the expected utility is greater than the certain utility. For example, her certain utility is minus 100 with a dialysis machine. Her utility will be minus 1,000 if she dies, and 10 if she returns to the level before the onset of her kidney disease. She will have the transplant operation with these makeup utilities. Let's do exercise 4.4. Robert Greene repeatedly and painstakingly applied herbicides to kill weeds that would harm his beet crops in 2007. However, in 2008, he planted beets genetically engineered. Roundup destroys weeds but leaves the crop unharmed, thereby saving a farmer thousands of dollars. However, this policy is risky. In the past, when beet breeders announced they were going to use Roundup-resistant seeds, sugar-using food companies objected, fearing customer resistance. Now, though, sensing that consumer concerns have subsided, many processors have cleared to plant the Roundup-resistant beets. A farmer like Mr. Greene faces risks by switching to Roundup-ready beets. Use a decision tree to illustrate this analysis that a farmer in this situation needs to do. Suppose the probability of being rejected by food companies is theta. We make up the utility under each possible outcome. The farmer has a utility of 30 if he does not switch to genetically engineered beets. If he switches, his utility will be 100 if his crop is accepted by food companies. His utility will be minus 100 if it is rejected. We can write the farmer's expected utility, EU. We compare it with its certain utility of not switching to genetically modified beets. Suppose the expected utility is greater than the certain utility. That is, if the probability theta is lower than 35%. Then the farmer is better off switching to genetically engineered beets. Let's go to exercise 4.5. In solved problem 16.6, advertising increases the probability of high demand to 80%. What is the minimum probability of high demand resulting from advertising, such that he decides to invest and advertise? The decision tree is as follows. Suppose the minimum probability of high demand from advertising is theta. We write the expected value of advertising, EV tilde. He chooses to advertise if EV tilde minus the advertising cost is greater than the expected value of not advertising. Theta should be greater than 65%. We add an arrow to the advertising path. Next, we consider whether he should invest. We compare the expected value of investing to not investing. Theta should be greater than 75%. As a result, the minimum probability of high demand from advertising is 55%. Advertising should raise the probability of high demand to at least 75% for a risk-neutral person to invest. Let's go to exercise 4.6. Because a state's governor can substantially influence new laws, uncertainty about the outcome of a gubernatorial election may affect whether firms make new investments. It's estimated that in a state with average partisan polarization, doubling the electoral uncertainty causes a 2.7% drop in manufacturing firms' investments. Explain a possible reason for this result. Does your explanation require that the firm's managers are risk-averse? Doubling the electoral uncertainty means the variance of the outcome increases. The graph shows that the two risky options have the same expected value, but option 2 has a larger variance than option 1. Option 2 has more uncertainty than option 1. The certainty equivalent of option 1 is CE1. The certainty equivalent of option 2 is CE2. The certainty equivalent is the certain value of wealth that gives the same utility as the risky option. A lower certainty equivalent indicates a lower election benefit for a risk-averse person. As a result, she will reduce her investment. A risk-neutral person does not consider risk. She only cares about the expected value. In our example, the expected value of the two options is the same. So, a risk-neutral person has the same utility in either option and will not change her investment. Let's answer exercise 4.7. A risk-neutral firm believes that the probability of a harmful cyber attack is 25%. It expects to make a profit of $200 million if no attack occurs and $120 million if it is attacked. The firm can spend $5 million to increase its electronic defenses. which reduces the probability of a successful cyber attack to 10%. Use a decision tree similar to figure 16.4 to assess whether the firm should make this investment. A risk-neutral firm aims to maximize its expected value because maximizing expected value maximizes its expected utility. The decision tree shows that the expected value of increasing defenses is 192 minus 5 equal to $187 million, which is higher than the expected value of not increasing defenses. So, the firm will increase its electronic defenses once it invests. We add an arrow to the path. Next, we consider whether the firm invests. The firm's expected value of investing is $187 million, which is better than not investing. We add an arrow to the path. As a result, the firm should make the investment and increases its electronic defenses. Let's solve exercise 4.8. R&D investments are a major source of business uncertainty. Do all risk-averse managers fail to invest in R&D? Why or why not? It depends on the utility function of the risk-averse person. Suppose the R&D investment leads to two possible outcomes. The firm earns Y dollars in the good state of nature and loses X dollars in the bad state of nature. The utility curve shows that the expected utility is EU. The certainty equivalent, CE, is the certain amount that gives a risk-averse person the same utility as the uncertain R&D investment. If the certainty equivalent is greater than the cost of the investment, then a risk-averse person should invest. Thank you so much for watching this video and solving all the exercises with me today. See you soon. Take care. Thank you for watching this video and subscribing to my YouTube channel. See you next time.